everybody, welcome back to another video. So today we're going to be going over the 2023 AP Physics 1 International Exam FRQ number 5 by request. And yeah, let's get right into it. So this question says that an object is released from above the surface of planet A, which does not have an atmosphere. The object falls towards the surface of planet A due to the gravitational field of planet A only, and the graph shows the magnitude of the acceleration of the object as a function of time until the object reaches the surface of the planet. And this is very important here. The first time that I did this problem, I did not fully read the question and see the second part. You'll see later on that sort of caused some trouble. And then I ended up having to try and calculate the area under the curve in a very, very weird way. But it ended up working, but I'll get more into that later. So what we want to do here is mark this up. So this area right here, region 1, will be the same as region 2 and the same as region 3. So all these regions are equivalent in area, and that's important to know. So let's see what the first question is asking. So the object is released from rest, okay, and reaches the surface of the planet at t equals 4,500 seconds. So this is when it reaches the surface of the planet, and they marked it up for us, which is quite nice. In addition to the information provided by the graph, which one of the following quantities is needed to calculate the magnitude of the net force exerted by the planet on the object? So let's see. Can we use Newton's law of gravitation, which states that the force is equivalent to the gravitational constant mass of 1, mass of 2 over the radius squared. Let's see. I don't actually think we can use this equation because we have way too many missing variables, right? We can only pick one of these quantities in order to get the unknown for, in order to calculate the net force. So we know the gravitational constant. We know big G. However, even if we find R, the radius of the planet, we don't know the masses of each of the planet or the object. And so at the end of the day, we cannot use this equation. So is there another equation we can use that has force in it? Yes, we do. And that is Newton's second law. Net force equals ma. You'll see this works out quite nicely because if we know the acceleration, because it's given by this graph literally up here, if we know this acceleration here, all we need is the mass, which is missing, in order to get the net force. And that mass is going to be of the object, because that object is the thing accelerating. And so here we can just pick mass of the object as the answer. All right, so part 2 says determine the ratio of the gravitational force exerted on the object by planet A at time t equals 4,500 seconds to the gravitational force exerted on the planet by planet A at time 2,600 seconds. So let's just write this out. So here t equals 4,500 seconds, t equals 2,600 seconds. And we're going to use that graph because we know net force equals ma. If we can find the acceleration for each of them, we know the masses are the same, and so they'll cancel out in the ratio. And so the ratio of the acceleration is really just the ratio of our net force. So here we can see that at region 3, at the end, 4,500, is it 4,500? Yep, 4,500 seconds is going to be right about here. And I would estimate that to be, it's on the higher end, just drew that line kind of bad. I'll say that's around 8.8. We're just marking that up to the acceleration. And then at 2,600, when it reaches the curve, that looks about 1.5 to me, 1.5 meters per second. So now we have our two variables. We can go back here and write acceleration equals 8.8 meters per second squared. Acceleration for 2,600 seconds is 1.5 meters per second squared. And then if we use Newton's, change colors, net force equals ma over net force equals ma. In reality, we can just get rid of the net force and just write ma over ma because it's the same thing. So This will be the first one for the 4,500 degrees. Second, sorry. That'll just be mass 8.8. And then mass is the same here over 1.5. We can see the masses cancel and we're left with a ratio of 8.8 over 1.5 as our final answer. All right, B wants us to determine the ratio of the speed of the object at time t equals 4,500 seconds to the speed of the object at time 2,600 seconds. So this is the problem I was talking about when I was didn't read this part here where all the regions were the same. So what I ended up doing was trying to estimate the area under the curve. But of course, these aren't perfect geometric shapes, like rectangles and whatever. So I had to do some very funky stuff. Ended up getting a pretty close answer, but now with this knowledge, and this is very key here, the area bound by the curve and horizontal axis is the same. We can easily solve part B. Something to note here is that it's asking for speed, and the graph of acceleration over time is equal to the velocity. Velocity is not the same thing as speed, right? However, in our case, because it's only accelerating in one direction, velocity is just speed with direction, right? So in our case, it really doesn't matter. We can use them interchangeably for now. All right, so if you want to find the ratio of the speed, we just have to find the area under the curve, because the area under the curve, as we said, is velocity, or really we can just use it as speed for now. So here, that this is just equivalent. This area is equivalent to region 2 and region 3. And so because of that, if region 3 accounts for all of this and this, right? Because region 3 is this entire thing. And so that's 3x regions. That's for the 4,500 second one, whereas our 2,600 second one was this only first region right here. And so this first region is really just 1/3 of the 4,500 second region. And so here we can write the answer as 3x the speed. All right, part C. So it says at a later time, the object is launched from the surface of planet A, so that it travels to planet B. The diagram shows planet A and B, the center of mass of the two planet system. The motion of each planet is negligible. So it wants us on this dot to label and draw the gravitational forces, not the components that are exerted by the planets. Each force must be represented by a distinct arrow, and they have to represent the relative magnitudes, but not the scale. So the scale basically means it doesn't have to represent the value of each of the forces. However, in relation to each other, they have to have the same proportion. So let's see here. So from what I can see, the center of mass is much closer to planet A than it is from planet B. All right. So using this information, I can detail Newton's law of gravitation, which is Fg equals a gravitational constant, mass of 1, mass of 2, over r squared. And r squared really here is just distance, but it's written as r squared. And so because of this, we know that a greater r, or a greater distance between our two objects, will lead to an exponentially smaller decrease in Fg. So increase in r will lead to a decrease in Fg that is much greater than any increases in mass. So planet A might be slightly greater than planet B, but since r is such a big value and it's squared in the denominator, that's going to make it a much smaller value comparatively. And so now we can just draw the forces. So force of B, we can just draw like this. The force of B, gravitational force. And the force of A just has to be much, much bigger. We can draw out like this. Force of A. All right, so the final part asks, as the object passes through the center of mass of the system, is the speed of the object increasing, decreasing, or remaining the same? So the speed here would be decreasing. Now why? Well, we have to look back at Newton's second law, which states net force equals ma, right? If we look at our forces on our free body diagram, the net force is in the direction of FA, right? Because FA is greater than FB, so net force is to the left. And since our motion, it said, where is it? The motion, wait, no. So it says it's launched from the surface of planet A and travels to planet B. So it's being launched and is traveling to the right, right? So it's motion. Motion is to the right. And that's also initial velocity is also to the right. However, the acceleration would be acting against that because it's to the left due to the net force. And so speed decreases. So yeah, that does it for this FRQ solution. If you guys learned something, make sure you subscribe. And if you have another question, make sure you leave it down in the comments below. Thank you for watching.